Okay, welcome people of the pre-seminar. We have Julius Benner, who's a local here at Charles, and he's going to give us an introduction to Hopf algebroids. Please.
Okay, thank you very much. Maybe at the beginning I should say I will not give the most general definition of a Hopf algebroid, but I give a definition that is most suitable for the in the context of differential operators, looking towards Miriam's talk. And in the end, I will also talk a little bit about Lie-Reinhardt algebras and their universal enveloping algebras. Okay, to get started, maybe a bit of motivation. So if you remember the definition of a Hopf algebra, so what was a Hopf algebra? So this consists of an underlying K module H. Okay, so for this talk, K will be a commutative associative ring with unit. Maybe if you're uncomfortable with this, you can think of K being a field, but this doesn't make the talk any easier. So I take it as a commutative ring. And then Hopf algebra consists of two parts. First, we have an algebra structure on A. So that means mu goes from H tensor H to H, and eta from K to H, the unit, such that mu is associative and unit. And then additionally to this algebra structure, we have a co-algebra structure. So here, delta is a map from H now to H tensor H. And epsilon is a map from H to K. And delta is co-associative and co-unitive. So I assume you know what these words mean. I don't have to explain them. And you want the following compatibility. You want that the coproduct is a morphism of K algebras. Maybe let me say, even though it's redundant, also the co-unit should be a morphism of K algebras. Okay, so at this point we have a pi-algebra, and to get a Hopf algebra, we also want that there exists map S from H to H, such that if I first do the coproduct, then either doing S tensor H and then multiplying, or the same thing where I do then this map S on the second component should give me eta composed of epsilon. So this such a map is called an antipode. Okay, so this is a Hopf algebra. Okay, now because as we will later see in the Hopf algebra, we don't necessarily, it's not so easy to define what an antipode is. It's more useful to look at this following characterization of the existence of an antipode, namely let H be a bialgebra. And then H is a Hopf algebra. If and only if the map from H tensor H to H tensor H, which sends H tensor G to first applying the copulate to H and then multiplying with G is bijective. So this map is called the Hopf-Galois morphism. Yeah. And we use this characterization to generalize. Okay. And now we have a Hopf algebra. What are we trying to generalize? Maybe can we replace the ground field K? Or the ground ring by an arbitrary let's say K algebra. And of course, if we do that, we probably want that H is an AA bimodule and that all the structure morphisms are bimodule maps. Okay, and now the first step towards this generalization will be A rings. So for simplicity in this talk, A will be commutative and also associative K algebra. And then I can define what an A ring is. This is essentially very simple. So an A ring R over an A ring R, let's say R eta consists of a K algebra R and a morphism of K algebras eta from A to R. And remark on this definition, this is the same, so an A ring R eta is, or maybe I should say the datum of an A ring is equivalent to a monoid in the category of AA bimodules. So if you have an A ring, then we can define a bimodal structure on R as follows. So this is an A ring. Then as an AA bimodule via A acting on R acted on by A prime, I define as eta A R eta A prime. And then the multiplication map vectors through. The balanced tensor product over A. And so can project down here. And get a map here. So this shows, explains how you take an A ring and get a monoid in A bimodules. And conversely, if you have a monoid, then you can simply take the unit map of this monoid, and this is such a unit map. So this is a ring or a K-ideomorphism. So maybe if you have read my abstract in maybe recall that I said we will be doing the setting where the source map is equal to the target map. And what this refers to is you can more generally consider not A rings, but rings over A tensor A op. And then you would have two sort of unit maps, and one is called source and one is called target. But in our setting, we only consider one. This is to say the source map is equal to the target. Good. Another definition. So this will again be an A ring and an augmentation or character on A, on R is a K-linear map epsilon from R to A such that if I first do eta and then epsilon, there should be the identity on A. And secondly, the kernel of epsilon is a left ideal. Maybe to understand this definition a little bit, so the datum of an augmentation on on R is equivalent to an extension of the regular left A modular structure on A. So that is, I have an action on A such that if I act with eta of A on an element A prime, then this is the same as A times A prime. Okay, and how do we see this? That this is equivalent to having an augmentation? Well, on one hand, in one direction, if I take an augmentation, then I can define the following action. Maybe let's write it like this. Then I can write A acting on R as I apply the unit map to A, then I multiply by R, and then I apply the augmentation. And you can check that this really gives you an action on A. And in particular, if I act with eta A prime on A. Well, this is epsilon of eta A prime, eta A. So this is because eta is an algebra morphism, same as epsilon of A prime A. This is A prime A. It's a good question. This would probably would be what one would define, but if you try to prove that this is an action, you will see it doesn't really work. I haven't thought about this computation in the preparation, but yeah.
Epsilon is just A linear, not A linear.
Here.
Yes.
Okay.
In particular, it's not a morphism of algebras. And so maybe naively you would guess you want to define a co-unit for Hopf algebroid, bi-algebroid, and you would define it as an algebra morphism, but this is not the correct thing to do. Sure.
So a small correction. So epsilon is left A linear, but not right A linear. And
okay, this is left.
Yes, it's so this being left linear is this description that acting on A on the left is equal to the multiplication. And another way to think of this augmentation is as a K-algebra map or as an A-ring map from R to the K-linear map of A to itself.
Yeah. Okay, maybe for the converse, if you have such an action and there's only one thing you can do, you could send R to R acting on 1, and this defines the character. I tried, but it goes up again. Yeah. Okay. Maybe I need to hurry up a little bit. So next, I will talk about bi-algebroids. Maybe again, the naive thing you would do is so an R-ring generalizes a K-algebra, and then you would put in you take some K module and put on it an A-ring structure and co-algebra structure and hope that these are compatible. But this is also a bit more difficult. Okay, maybe I give you first a wrong definition. So a bi-algebroid H over A is an A-ring H comma eta plus plus an A co-algebra structure on H. So here I take the left A modular structure given by the unit map on H, and then I can define what a co-algebra is. So a co-algebra over H. And then such that Okay, and here we have to be careful. This is not the balanced tensor product where I take the right action here and the left action here, but I take actually the left action on both sides. And I wanted this is an algebra map. Let's say algebra map. And the problem here is this guy here is not an algebra in an obvious way, maybe. Maybe what the difficulty is. So I could define the product here as just component-wise as you are used to for tensor products, but then if I would multiply maybe an element like this, H1G1 times H2, and let's say A times H2 by A, some element in A, G2, then this should be the same as H1G1 because I'm over the balanced tensor product here times H2 AG2. But this guy up here, this is H1 A H2 tensor G1 G2, while this guy here is H1 H2 tensor G1 A G2. And so you see there's no way to bring this A across here. And to circumvent this, we will consider a subspace of this balanced tensor product. Yeah, that's a bit confusing. But in this definition, I take the structure H delta epsilon as a co-algebra over the ring A. And think of maybe in your head replace A by K, and then if you do that, you only have a balanced tensor product over left modules, right? And that's why I also take the balanced tensor product over left, over the left modules in this definition.
Take a different action, you see that you have the same problem because then you would have to move the A also to the right, for example, or something. Yes, it's not that we got to.
Okay, maybe the solution is actually very simple. You just take all the elements where this does, like where you can bring the A across as you would like to. And this is the Takeuchi product. This is denoted by, so H is the same as before. It's denoted by this A times subscript AH. And this is all the elements HI tensor GI in this balanced tensor product. Such that when I take any A in A, I can bring it across. So HIA tensor GI is the same as sum over I HI tensor BIA. Okay, now I can give it a correct definition. And this should be due to Svila in 74, and later this was generalized by Takeuchi in 77. So a bialgebroid over A is an A ring H eta plus a coalgebra structure. H delta epsilon on H such that the coproduct restricts to a morphism A rings from H to the Sakeuchi product. And secondly, epsilon is an augmentation. I'm almost running out of time. Okay, to wrap up, I give you the definition of a algebroid. Okay, and this uses the Hopf-Galois map I just erased. And so, and this definition is probably due to Schaunborg. So let's phrase it like this: by algebroid H is called Hopf algebroid if the map now this goes from the balance tensor product where you consider the right A action on this left vector to this other balance tensor product. And this, yeah, it's defined the same way as before. It sends G tensor H to delta GH. And this should be bijective. Okay, do I have time? Maybe I talk in the last 2 minutes a bit about Lie-Reinhardt algebras. But I don't, there's no time to give the definition, but maybe you already know what it is. This helps you. So if L, comma A is a Lie-Reinhardt algebra or Lie-Reinhardt pair, then one defines its universal enveloping algebra. And this is a Hopf algebroid. So how does this thing look? So in a Lie-Reinhardt algebra, L would be a Lie algebra and is a commutative K algebra. And this guy is generated by the tensor algebra of L and A. So you can build a universal K algebra that contains these two guys, and then you factor out the relations xy minus yx equals the commutator of L, then xa minus ax equals this thing here. So Lie-Reinhardt algebra always has an anchor morphism which goes from L to the derivations of A, which is a left A linear and the morphism of Lie algebras. And then lastly, in this universal developing algebra, I have the relation that Ax is the same as acting by A on X. So at least even if you don't know exactly how this looks like, just remember that this is just generated by Lie algebra elements. And so to define a coproduct, I just have to tell you how this acts on the Lie algebra elements. And this is the same as in universal developing algebras of Lie algebras. You just make them primitive, and then a co-unit kills these elements. Okay, and why am I talking about these Lie-Reinhardt algebras? What you can always show is if you take any K algebra A and look at its derivations and take rho to be the identity map, then this is a Lie-Reinhardt algebra, and you can construct this huge thing here, this universal developing algebra. And in good cases, when the algebra A is smooth, this is isomorphic to the differential operators on A. And with this remark, I'm finished.
Other questions?
Is it clear that this is always non-empty, the Takeuchi product?
Well, you have this guy in here.
Good point. Okay, so non-unital elements.
But it's not so clear if it can be very small. It's not so easy to figure out what this is.
Moving quickly on. So what was the contribution of Sweetler that Takeuchi built on, or did they just not know?
I think Sweetler was okay. I'm not quite sure, but Sweetler was the first one who looked at these kinds of things. And
the Takeuchi product was introduced by Sweetler.
Yeah.
Okay.
But Takeuchi, of course, generalizes for arbitrary rings, not just for commutative ones. Yeah.
Just in the spirit of what we've been talking about, is there some Lie-Reinhardt co-algebra where you're going to co-derivations?
Probably they are. Just reverse the arrows, right? I don't know.
And then when like in the limiting case of when you go back to a field, the Lie-Reinhardt reduces to a Lie algebra, and this is the universal enveloping algebra of the Lie algebra.
Yeah.
Okay, thanks.
More questions? Yeah, I have a question, and behind my question there are like 10 other questions.
Whoa,
so
okay.
the easy one is, do you know if there is some quantization factor from Lie by algebroids to Hopf algebroids such that?
So what
Yeah.
would a Lie by algebroid be?
This is one of the 10 questions. So there is a quantization factor from Lie by algebras to Hopf algebra. So one could ask if you can extend the functor to oids.
Mhm.
I was just
Yeah, that's a
asking everybody if you know
good
something about it.
direction. Yeah, but I mean, this relates to Ray's question. Is there a Lie-Reinhardt co-algebra? And you probably would need this, and then you find what the Lie-Reinhardt bialgebra is, or the bialgebroid. I don't know if people have done this.
Mm-hmm.
And yeah, then you could start working on that.
Yeah.
But I don't know if people have looked at this.
Among the 10 questions, there is also, do you know if it makes sense to deform a Hopf algebroid? This is one of the things you need, no? To talk about. So in the class, H bar deform. Topological Hopf algebroid, I would say. So we take a formal power series of Hopf algebroid and look into first order deformation, second order, and so on.
Okay.
Yeah.
I don't know if there's a general notion of deformation, but maybe I can tell you something interesting related to this. If you have if you start with the Lie-Reinhardt algebra L, then you can look at the tensor algebra now using balanced tensor products over A. In good cases, if your Lie-Reinhardt algebra L admits a connection along itself, then you can define a new product which is called diamond for some reason on this guy. And if you look at a pair and the tensor algebra of this new product, so I would say if there's a connection. How did it work? Maybe like this. You can look at this new K algebra, and you can show that this is isomorphic to the universal enveloping algebra, not of the Lie-Reinhardt algebra L, but of the free Lie-Reinhardt algebra of L, where you forget the Lie bracket, or the same algebra A. And then you can locate a certain ideal in this guy, and if you divide it out, you get back the universal enveloping algebra of L. And this was done by Araujo in 22. And you can use this to show a Poincaré-Birkhoff theorem for these Lie-Reinhardt algebras.
Okay, more question, maybe also from the online people. If you have a question, just unmute yourself and ask the question. If not, let's thank Julius for his great talk. Thank you. Now we have a short break and then there's the main seminar.